Figure 9.14 shows us the association between, or the reaction between, soil pH and a lot of soil nutrients, as well as some soil microbial functions. So at the very top you can see the reaction, or actually in this case the lack of reaction, by fungus or fungi to soil pH. And in the range that we typically see in soils, there's not really a reaction. There might be a reaction in terms of the kind of fungi that's seen, but not in the amount of fungi seen. Contrast that with the bacteria, where at the low end of pH in the soils, you see a reduction in the number of bacteria that are active in the soil. Now, the next chapter we'll get into soil microbes, but right now you just need to know that there is that relationship between a lower pH and a lower number of bacteria. As you can see with nitrogen, potassium, sulfur, calcium, phosphorus, molybdenum, copper, and boron, the relationship is again negative. So when we have a lower pH, we have less availability to plants of these nutrients. So really, we're thinking about the ability of plants to quote unquote see these, or to take them up as plant nutrients. We have other ones that become more available. So typically, if that is the case on the low pH end, for something you can see like molybdenum, you have a higher availability at the high pH end. For these up here, nitrogen, potassium, and sulfur, not so much. There's some interesting things going on right in here with calcium, magnesium, phosphorus, iron, and manganese. And that's because phosphorus has a really interesting relationship with calcium and magnesium at high pHs, and iron and manganese at low pHs. And what you're seeing here, these little gear-looking things here, are the fact that when phosphorus is found at high pHs, it's typically found as joined with calcium and magnesium. And in those situations, it's typically a little bit harder to get at the phosphorus for plants. It's not as available as it is in neutral or slightly acidic pHs. The same thing when you move down to the acidic end with phosphorus, it becomes what we call complexed with things like iron, and this makes it unavailable to plants, so that plants can't, again, quote unquote, see the phosphorus that's there. Another interesting thing here, we have iron, and as you move towards the high pH end, iron becomes very unavailable, not available to plants, and you often see at high pHs, for instance, with something like soybeans, this iron and manganese deficiency happens at very high, at higher pHs, because iron is less available. So we see that plants are telling us, by the way their leaves react to a lack of iron, that they have an iron deficiency, and we can see that in plants, and plants can tell us those sorts of things. So this is really, when we talk about pH being a master variable, we've seen how pH can affect CEC. We're looking at how pH can affect living organisms in the soil. We know pH can affect if roots are stunted or not. And now what we're seeing is pH can affect the availability of nutrients to plants. So again, this quote-unquote master variable means that pH is a very important reading. In fact, a lot of soil scientists say, if I could only measure one thing about a given soil, if you plopped me down in the middle of Russia and said, you need to tell me something about the soil, if they could only have one measurement, they would choose pH, because it gives us so much information about where we are on the spectrum, about the availability of plants to grow there and or not, and those sorts of things. So again, another reason why pH is a very important reading that we get from the soil.